Welcome back to the Deep Dive. Today, we're really honing in on the absolute foundation of modern defense. We are focusing exclusively on the essential building blocks of cloud security.
Right, we're talking about identity and access management.
Exactly. We are going way beyond the old idea of a firewall and looking at the very specific rules that govern who or, what is allowed to even interact with your cloud environment.
That's the critical shift, isn't it? I mean, when organizations first move to the cloud, they have this realization that the traditional network perimeter, that big static firewall,
Yeah, the fortress wall.
it's virtually meaningless. Every single resource is accessed with an API call, and that call could come from anywhere on the internet. If you're only relying on network rules, you're leaving the doors wide open.
So if the wall is dissolving, if it's not there anymore, what becomes the new hardened security perimeter that we have to rely on?
The new perimeter is unequivocally identity.
Identity.
100%. It's all about ensuring that every user, every microservice, every virtual machine, I mean, everything that tries to do something can prove exactly who it is.
And then what?
And then the system has to strictly enforce what that proven identity is actually permitted to do. This brings us to the core narrative for this deep dive. We're calling it the bouncer.
The bouncer. I think that's a really, really helpful metaphor, especially for anyone trying to wrap their head around this for the first time. Security isn't this passive wall anymore. It's an active enforcement mechanism that's constantly checking credentials.
Exactly. Imagine a high security building. The bouncer isn't just standing at the front entrance. There's a bouncer at every single internal door, checking your ID and your permissions before letting you access a resource or a sensitive area.
So it's constant verification.
Constant. And we have to address three core questions that this bouncer is always asking. One, is this identity legitimate and verified? Two, based on that ID, what specific doors is this identity allowed to unlock? And three, are there global rules for the entire building that override all the individual permissions?
That sets up our mission perfectly.
Yeah.
So we're going to spend this time unpacking the fundamental differences between, say, permanent and temporary access keys. We'll clarify the distinction between those high-level organizational rules and the specific individual permissions.
And we'll show, with practical examples, why giving any identity even one bit more access than it absolutely requires is just the fastest way to cause a security failure.
Let's start with what has to be the most dangerous rookie mistake in the entire cloud security playbook.
Okay, let's do it.
Our source material's just crystal clear on this. The biggest initial threat, particularly for newcomers moving workloads to the cloud, comes from the misuse or compromise of long-lived credentials.
Specifically for machine identities, for service accounts. If you get one thing right today, this is it. You have to avoid this risk.
This is ground zero of cloud breaches. I mean it. Attackers don't need to hack your firewall if you just leave the door keys lying around.
Right.
And when we talk about these long-lived credentials, we're really talking about what we call the physical metal key.
The physical metal key.
The JSON service account key.
Okay, can you elaborate on that? For those who are just starting out, what exactly is a JSON service account key, and why is it so much more dangerous than, say, a standard password?
Sure. So a JSON service account key is a cryptographic key pair. You usually download it as a file, a simple file.
A file on your laptop.
A file on your laptop, a file on a server. And this file, this is the critical part, it contains the private key material. Once it's generated, that key file acts as a permanent, standalone authentication credential.
Permanent.
It grants access to your organization's resources indefinitely, or, well, at least until you remember to go in and manually revoke it. And when you say permanent, we really need to stress that this key doesn't live securely inside the cloud environment. It's a downloadable asset. Right?
That is the absolute core of the risk. Once that key file is downloaded, maybe to a developer's laptop or a CI/CD server, or it gets embedded in a container image, it is now outside the cloud provider's direct control.
It's in the wild.
It's in the wild. If it's lost, copied, stolen, or accidentally committed to a public GitHub repository, which, by the way, happens with terrifying regularity.
I've heard stories.
Oh, yeah. It works forever. It's like a skeleton key that never expires, and it grants whatever high-level access the service account was initially given. And since new users often assign overly permissive roles to these keys...
Like editor.
Exactly, like editor. The blast radius, if it's compromised, can be huge. It could lead to immediate data exfiltration or, just deleting all your resources.
The moment that key leaves the secure perimeter, you've lost control. And you have no idea when or even if an attacker might use it. That just seems like a completely unacceptable risk for modern security.
It absolutely is, which is why the industry standard and the Google recommended best practice is to switch entirely to what we call the hotel keycard model.
The hotel key card.
Right. This leverages modern, short-lived identity practices, primarily something called workload identity, especially in dynamic environments like Google Kubernetes Engine or GKE.
The hotel key card analogy is so powerful because the operational difference between that metal key and the card is just fundamental.
Yeah.
I mean, if I lose my actual car key, it's a disaster. I have to call a locksmith, rekey the car.
That's a whole thing.
It's a whole thing. But if I lose my hotel key card, it probably won't even work 2 hours after I check out, if it works at all.
That is the principle. Credentials issued through workload identity are ephemeral. They're short-lived.
Ephemeral.
They're just temporary tokens issued only to an authenticated workload for a very brief window of time, often just minutes. If that token is stolen, the attacker only has access for that limited period.
And then it just expires.
It expires, and a new one is automatically issued to the application. So the window of exposure is minimized from, potentially years down to mere minutes.
Okay, let's get a bit technical for our learner audience. If someone is setting up a continuous integration system, a CI/CD pipeline, maybe running builds inside a GKE cluster, which is a super common pattern, how do they correctly implement this hotel keycard system using workload identity? Because I hear it often gets skipped because it has a few moving parts.
It does. It requires 3 distinct but coordinated steps. But these steps are what ensure that secure chain of custody.
Okay, what's step 1?
Step 1. You create a specific Kubernetes service account inside your GKE cluster. We have to remember Kubernetes has its own identity system. A pod, which is just the smallest unit that houses your application container, it runs under the context of this local Kubernetes service account.
So that local service account is the identity just within the Kubernetes world itself.
Precisely. Now, step 2. You create a separate Google service account. This one is outside the cluster. This is the core identity that's recognized by Google Cloud's IAM system.
The real identity, in a sense.
The real identity, yeah. And you grant this account the appropriate minimal IAM permissions, the door lock that it needs for its job, like maybe being able to push images to artifact registry.
Okay, so we have the Kubernetes identity and the Google Cloud identity. What's step 3?
Step 3 is the magic. You use workload identity to securely link those 2 accounts, the Kubernetes one and the Google one. You do this by creating an IAM policy binding that allows the Kubernetes service account to impersonate or act as the Google service account.
That handshake is the genius part. So when my application runs in its pod, it presents its local Kubernetes ID and Google Cloud because it sees that verified link. It issues that temporary short-lived token, the hotel key card, which lets the pod do its job as the Google service account.
That's exactly how it works. The actual key material, the private key, never needs to be stored or downloaded or managed by the user. It all stays within Google Cloud's controlled system. It just fundamentally minimizes the entire risk surface compared to managing a static file.
This sounds essential, but I can see how if you're pressed for time or you're new to the system, it's just easy to fall back into old habits. What does the anti-pattern look like? The thing to avoid?
The anti-pattern is what we call trying to hide the permanent metal key inside the perimeter.
Okay.
So a beginner realizes they need Google Service Account access. So what do? They generate the JSON service account key, they download it, and then they store that permanent file as a Kubernetes secret.
Which sounds secure, right? It's called a secret?
It sounds secure. And then they inject it into the pod through an environment variable, often named something like Google Application Credentials.
So, okay, they successfully put the key inside the fortress, inside the secure Kubernetes environment.
Yeah.
Why is that still fundamentally a dangerous metal key?
Because the credential itself is static and long-lived. If the cluster is compromised, maybe an attacker gets read access to the Kubernetes secrets, or if that specific secret is accidentally exposed, that permanent key is now in the hands of the attacker.
Regardless of how short-lived the pods are.
Exactly. That key can be taken outside the cluster and used against any resource the service account has access to indefinitely. You've secured the location, but you haven't secured the key itself.
So the recommended practice is to not use Kubernetes secrets to store the key, but maybe for other runtime configuration, while the authentication is handled just by workload identity.
Absolutely. The goal is to move beyond static secrets for authentication altogether.
Now let's address reality. Not everyone is running on GKE. A lot of listeners still rely on traditional VM infrastructure. What about older systems like a Jenkins CI/CD server just running on a compute engine VM? We can't use workload identity in the exact same way. So how do we apply that hotel keycard principle there?
That's a crucial point. The principle still holds. Leverage the identity the infrastructure provides you rather than creating a portable static key.
Okay.
The recommended practice for a Jenkins server or any application running on a compute engine VM is to make sure the VM instance itself has an attached service account with the right permissions.
Attached to the VM itself.
Right. When a VM starts, it's automatically granted a unique inherent identity token. Any application on that VM like Jenkins can automatically use that instance identity to authenticate with Google Cloud APIs. It avoids the whole mess of downloading, storing, and manually securing a static key file on the server.
So if that Jenkins server gets breached, an attacker only gains access to the temporary permissions granted to the machine, and only while they're on the machine.
Right.
They don't get a portable JSON file that they can take and use from their own desktop later on.
Precisely. If the attacker leaves the VM's identity stays with the VM. It dramatically reduces the risk of credential theft and, lateral movement outside the compromised machine. Always, always use the attached instance service account for VMs. Don't use manually managed keys.
It just sounds like it reduces management overhead and makes everything more secure.
It does. It's a win-win.
Okay. So we've established that the bouncer needs to verify your identity, and that identity should ideally be a short-lived hotel keycard. Now we have to move on to how the bouncer decides what you can actually do once you're inside. This is where a lot of newcomers get tangled up, the relationship between IAM, identity and access management, and organization policy. They both seem to govern access.
They do, but they operate at completely different levels of granularity, and they serve fundamentally different security roles. This distinction is just vital for setting up effective cloud governance. Let's formalize them.
Okay.
Let's call them the door lock versus the zoning law.
The door lock versus the zoning law. Okay, let's start with the fine-grained control. IAM as the door lock. What's its core function?
IAM is the system that grants specific rights to specific identities. It answers the question, what exact actions is this person or this machine allowed to take? It's authorization in its purest form, it's super flexible, and it applies at the project or even the resource level.
So if I'm an application developer, IAM dictates that I have the key to deploy code to my staging environment, but not the key to delete the production database.
Exactly.
It's a specific key for a specific door.
That's the perfect way to put it. And if we go back to our earlier example, granting a compute engine service account, the logging.logwriter role is a perfect example of a specific door lock.
Right.
It gives the application the granular ability to write log entries to cloud logging, its only job. And it explicitly denies it permission to do anything else.
Here.
If you try to do something outside of what that lock allows, IAM just says permission denied.
Now, let's contrast this with the big picture. Organization policy as the zoning law. If IAM is about granting permissions, what on earth does org policy do?
Org policy is about setting mandatory preventative constraints across your entire enterprise or, big folders full of projects. It doesn't grant permissions at all. It actively establishes rules that no one is allowed to violate, regardless of what IAM roles they have.
So it's an override.
It's an organizational override. It's a governance mechanism.
Okay, so if IAM gives the administrator the key to build anything, they have the right door lock. But the org policy, the zoning law, says no one is allowed to build resources in the U.S. region. Then the zoning law wins.
The zoning law always wins. The administrator's IAM permissions are just rendered moot by that higher-level organizational rule.
That's a powerful concept.
It is. Org policy is the iron fist of the bouncer applied globally. It enforces immutable rules. For instance, an org policy might require all new virtual machines to have shielded VM enabled for integrity monitoring.
Right.
Even if a project owner has full IAM permission to create a VM, the org policy will block the creation unless shielded VM is activated. It's preventative security at a massive scale.
This distinction is so crucial because it lets us tackle that core security problem we talked about, the dangerous metal keys. Not just by, educating users, but by forcing a secure behavior. How do we use the org policy, the zoning law, to just eliminate the risk of long-lived service account keys across the entire company?
This is, and I'm not exaggerating, this is arguably the single most important policy you can enforce for cloud governance. The essential constraint is called constraint.cm.disable service account key creation.
Okay.
And the goal is simple and powerful. You apply this constraint to your organization node, the very root of your resource hierarchy.
And by doing that, you're basically declaring organization-wide, we do not trust static keys. We are completely banning the ability to mint a new metal key. Is that right?
That's exactly right. And the beauty of this organizational mandate is that it forces all developers and all applications to adopt the safer hotel keycard approach workload identity or attached instance service accounts.
It forces the good behavior.
It forces it. And this is where you get significant operational relief. Instead of having to run expensive manual key audit tools across hundreds of projects every month to find forgotten keys, you just eliminate the source of the risk entirely. At creation time, you remove the insecure path as an option.
That operational relief, that's a huge insight for our learners. It's not just about security. It's about reducing the audit burden by designing security in from the start.
Precisely. Governance shouldn't feel like you're constantly chasing exceptions. It should be about setting smart defaults.
But the real world is messy. So what happens when a third party or a legacy piece of software absolutely needs a JSON service account key to function, and your organization has enforced this constraint globally? The developer tries to create the key and gets that error.
The organization policy constraint is enforced.
Yeah, what do you do?
This is the moment where security maturity is really tested. The impulse for an organization under pressure is to just globally remove the constraint, which instantly compromises every other project for the sake of one legacy app.
Right, the easy way out.
The easy way out. The recommended prudent security practice is to maintain that protective zoning law for the rest of the organization, for the 99%, and create a highly controlled surgical exception.
So how do we perform that security surgery?
You use the hierarchy that's built into the org policy system. You keep the constraint on at the organization or folder level, but you apply an override rule to set the constraint to off only in that single specific project that houses the necessary third-party application.
So you limit the blast radius of the exception.
To the smallest possible unit. This strategy shows that you understand the rule, you respect the security posture, and you're handling necessary exceptions with precision and accountability rather than just caving to operational pressure. You're saying, the rule stands for the whole building, but this one room has a special documented exemption.
That organizational discipline is key. It lets development move forward while keeping that high baseline security posture everywhere else. Okay, now let's shift our focus to the decision-making philosophy of our bouncer. The principle of least privilege. It sounds simple, only grant the minimal permissions necessary, but actually doing it right in the cloud, where roles are complex, is notoriously difficult.
It's difficult because granting broad, excessive permissions, it often works instantly, while figuring out the exact minimal role takes thought and, sometimes trial and error. But the cost of that convenience is an unacceptable level of risk.
Right.
Giving a service account the editor role because it's fast is like giving every temporary vendor the master key for the CEO's office and the server room. You just think do it.
Let's use the cameraman analogy based on the cloud logging scenario. This is a classic operational task. We have a security analyst or a DevOps team member who needs the ability to configure where logs are exported. They need to set up a log sync.
Right, sending them to a storage bucket or maybe a security information and event management system, a SIEM.
And for our new listeners, a SIEM system is what?
A SIEM is, it's essentially a centralized command center. It gathers, analyzes, and manages security-related events from all your different logs and systems. It's where your security team looks for threats.
Perfect. Thank you for defining that. So back to our analyst who needs to set up this export sync. Why shouldn't we just give them the basic, easy editor role on the project? It would definitely let them configure the log syncs.
We have to think about the risk of over-granting the blast radius. The editor role is one of the highest roles you can give. It provides permissions to modify or delete almost every resource in the project, compute engine instances, networking rules, databases.
The whole shebang.
Everything. Their job is just to configure the cameras, the log system. The editor role gives them the power to demolish the building, accidentally or intentionally. That's just entirely disproportionate to the task.
So what is the prudent minimal role? The key that only opens the door to the camera configuration panel.
The correct IAM role here is logging.configwriter.
Configwriter.
Right. This role specifically grants the ability to manage log syncs and exports, which is exactly what the job entails. It lets them configure where logs go, but it prevents them from managing VMs or altering application code or deleting other project resources.
That is a critical distinction. They are writers for the configuration of the logs, not writers for the content of the logs or writers for the underlying infrastructure.
And this attention to detail saves organizations from massive, avoidable outages. If you grant editor, a simple typo in a script run by that analyst could wipe out your production infrastructure even if their intent was totally innocent. Least privilege is a hedge against human error just as much as it is against malicious intent.
We should probably also address the other side of logging. The application actually writing its data. What's the minimal role needed for a service account attached to a compute engine instance to successfully write its application logs to cloud logging?
That requires the fundamental logging.logWriter role. This is the permission to execute the action of inserting a log entry.
Okay.
This is critical because if that service account is attached to the VM but it lacks this specific permission, the application will generate the logs locally, but they'll never successfully reach cloud logging.
And the operational consequence of that?
Immediate security blind spots. If your app is running but it can't write its logs, you lose all visibility into errors, performance issues, security events. So if you're debugging a new VM and you see 0 logs in the console, the first place you look after checking the networking should always be the attached service account to make sure it has the logging.logWriter door lock.
Let's extend this principle to managing read access for sensitive logs, secure log viewing, and segregation. We often have organizational rules where different teams need different levels of visibility.
Absolutely. Think about a company's security team. They need read-only access to the most sensitive data, the audit logs, which are stored in that non-modifiable required bucket. The approach here has to be very tightly controlled.
So what's the least privilege approach for giving that team read access?
First, we grant the specific read-only role. Roles logging.private log viewer. This is necessary for viewing audit logs. Second, and this is just as important for operational security, we should never grant this role to 50 individual team members. We grant the role to a Google group that contains all the security team members.
Why is granting permissions to a group so much better as a security practice than granting them to individuals?
It dramatically simplifies lifecycle management and reduces operational overhead, which itself is a key security risk in large environments. When a security engineer moves to a different team or leaves the company, you just remove them from the group.
And the permission is gone.
Immediately. It's centralized. If you had granted the role individually across dozens of projects, you'd have to manually hunt down and revoke every single binding. That process is so prone to error, and you could easily leave orphaned access credentials lying around.
That's a huge operational win. Now let's tackle the challenge of centralized logging. An organization collects all application logs from projects A, B, and C into one central logging project.
Very common.
The requirement is strict. Project Team A must only see their logs. Team B must only see theirs, but the central operations team needs to see everything for troubleshooting.
This is a perfect real-world scenario for implementing resource-based filtering using log views.
Log views.
The solution is to create specific filtered log views within that central logging project. For Project Team A, you create a log view that applies a filter, ensuring it only displays log entries that come from Project A. For example, the view might only show logs matching the label resource.labels.projected project alpha.
Okay.
You then grant the read-only log viewer role to the group representing Team A, but you only granted access to that specific log view. They can't see the raw, unfiltered logs.
So we're slicing the central data lake based on need, ensuring absolute segregation of data. What about the central ops team who needs the full picture?
The operations team, the one that requires full oversight for critical diagnostics, they get granted access to the central logs view. That's the default unfiltered view of all the gathered logs. This strategy maintains least privilege for the development teams while ensuring the ops team has the necessary scope of access. It's also far more cost-effective and operationally simpler than alternatives, like exporting logs into separate BigQuery tables for each team, which can get really expensive and redundant fast.
This just shows how these fine-grained IAM roles, when you combine them with logical resource organization like log views, create a secure, segregated, and highly efficient logging architecture. Okay, so our bouncer has established the identity of the people and machines and defined their boundaries. Now they have a new task, checking the identity and integrity of the shipments.
Right.
The actual code and container images being deployed. We need security mechanisms that ensure the code itself is authorized and safe.
This moves us into shift-left security, enforcing policy much earlier in the development lifecycle. We have to prevent developers or automated systems from pushing compromised, vulnerable, or just unauthorized code to sensitive environments, like a production GKE cluster.
The first mechanism for checking the shipment manifest is binary authorization, BinAuth. What specific problem does this solve in a modern CI/CD pipeline?
The problem is bypassing quality gates. Developers might forget to run a vulnerability scan, or an operator might manually deploy a build that failed a critical load test just to fix an outage quickly.
Been there.
Binary authorization is the deploy time gatekeeper. It enforces a security policy specifically at the deployment stage in environments like GKE. When a user or a system tries to deploy a container image, the cluster's admission controller, our physical bouncer at the cluster door, intersects the request.
Okay.
It then checks the image's manifest to see if it carries the required digital attestation.
Attestation. For our audience, that's just a fancy word for a verified signature, right?
Yeah.
Proof that the shipment passed inspection and was signed by a trusted authority.
Exactly. It's the digital seal of approval. If the image lacks the required signature, the deployment is blocked immediately. It just returns an error saying the image is unauthorized.
What does that enforcement policy look like in practice? How does BinAuth know which shipments to allow?
We use two main checks based on the source material. First, we check the origin. The policy can be configured to whitelist the image name pattern. This ensures you only accept images coming from your official, trusted repository.
Right.
So the policy might strictly allow only images from, say, artifactregistry.io, your official repo. If an operator tries to deploy an image pulled directly from an unauthorized public Docker hub, the bouncer just rejects it instantly.
And the second check?
Second, and this is more robust, we check the signature, the attestation. The policy requires that the image must be signed by one or more trusted entities within your CI/CD pipeline, certifying that key processes like security scanning, unit testing, or load testing have all successfully completed.
That brings us to trusted signing and CI/CD attestation. Let's focus on the scenario. We need to ensure that only builds that pass a rigorous automated load test are deployed to production GKE. How is that seal of approval, the attestation, created securely, tying back into our identity principles?
This is where we combine identity management with cryptographic signing. The attestation must be created using a private key that's stored in Cloud Key Management Service.
Cloud KMS, let's define that for our audience.
Sure. Cloud KMS is Google Cloud's highly secure managed service for creating, managing, and using cryptographic keys. Keys in KMS never leave the service unencrypted, which offers maximum protection. And the keys are organized into a keyring, which is basically just a logical container for keys in a specific location.
Got it. So we store the private signing key in KMS. How does the automated build system, the one running the load test, get access to use that key without storing a static key file itself?
We leverage workload identity.
Of course.
The service account associated with the build system is granted the specific IAM permission to use the key in KMS for signing operations. The build system, verified by its workload identity, requests KMS to sign the attestation metadata, confirming that the image is approved.
And this is critical because it confirms that the trusted automated system signed the code.
Right. It prevents developers from manually creating fraudulent attestations with a portable key, or prevents system compromise if a static key were stolen from the build server. Strong identity is the guarantor of code integrity.
Okay, so before the bouncer approves the signed shipment, we need quality control for known flaws. We need to check for the digital equivalent of, rust or mold on the shipment.
That's vulnerability scanning. Before signing and deploying, you have to integrate container analysis into the pipeline. This service automatically scans container images stored in Artifact Registry or Container Registry and reports any known common vulnerabilities and exposures, CVEs, that are present in the image's layers.
So even if the code was built by an authorized identity, if the underlying operating system or library contains severe unpatched vulnerabilities, container analysis flags it. And that could potentially stop the attestation and block the deployment.
Exactly. It ensures that the integrity check goes beyond just, was it built correctly, to, is the resulting artifact safe to run?
Now that the code is authorized, we have to talk about handling sensitive cargo. Application secrets like database credentials, API keys, passwords. We established that embedding these directly in the code or containers is a massive risk. So Secret Manager is the solution, but how do we implement it for different needs?
Secret Manager provides a centralized, encrypted, auditable location for all secrets, and we can look at three distinct patterns based on application needs.
Okay, pattern one.
Yeah.
A standard cloud-run application needs a static API key for a third-party service. It doesn't rotate often.
The secure recommended method here is simplicity itself. You save the API key in Secret Manager. Then, during the Cloud Run configuration, you reference the secret as an environment variable.
Right.
The application's service account is granted the IAM permission-secretmanager.secretAccessor to fetch that secret. The secret is only exposed to the application instance at runtime via the environment variable, keeping it out of the code and repository.
Okay, simple enough. Pattern two. High-frequency rotation. An application needs a database password that rotates every 24 hours, and it cannot afford any downtime for restarts. Injecting it as an environment variable at startup won't work here. Why is that, and what's the fix?
It fails because environment variables are static for the life of the running process. If the password changes in Secret Manager, the running container is still using the old environment variable value until you restart it. For zero downtime rotation, the fix is to store the password in Secret Manager and mount the secret as a volume within the application container.
Mount it as a volume, meaning it appears as a file inside the container's file system.
Correct. Secret Manager can project the secret content as a file into a volume mounted inside the running container. Crucially, when the secret rotates in Secret Manager, the projected file is dynamically updated inside that volume without requiring the container to restart. The application is designed to periodically read the updated password from that file path, ensuring it's always using the latest credential with zero downtime. This is essential for highly available stateful services.
That dynamic update capability is a huge advantage for operational reliability.
And finally, pattern 3. Secrets needed during the build process itself. Specifically, database credentials necessary for a cloud build pipeline to run integration tests against a database. We can't store the plain text credential in the source repository.
So if Cloud Build needs database credentials to run a test, what's the best practice?
We use Cloud KMS to encrypt the plain text secrets, and we include that encrypted blob, that ciphertext, in the deployment configuration or build definition file. The sensitive data is encrypted at rest right there in your source code repository.
Okay, and the final step.
The final step involves IAM. We grant the Cloud Build service account specific IAM access to the KMS keyring necessary for decryption. During the build process, Cloud Build fetches the configuration, uses its authenticated KMS access to decrypt the secret in memory, uses the plain text secret for the integration test, and then, this is the most important part, it immediately discards the plain text secret. It's never written to disk or logged, ensuring the secret is only exposed to memory for the brief moment it's needed.
Wow. We've covered everything from basic identity to complex code integrity checks and granular secret management. It's just overwhelmingly clear that every single security choice we make ties back to a foundational decision about how we manage and grant identity.
We certainly have. We successfully navigated the critical importance of abandoning that static, vulnerable physical metal key for the dynamic, secure hotel keycard approach enabled by workload identity. We clarified the hierarchical power of organization policy as the zoning law, which sets guardrails that override specific IAM door locks. And we saw the principle of least privilege applied to critical operational tasks, ensuring a minimal blast radius.
The central lesson, I think, from all of our source material today is that the old model of defending a network edge is just obsolete in the cloud. If an attacker compromises an identity, be it an overpermissioned service account or a stolen user key, they bypass virtually every other security control you have. It doesn't matter how complex your network segmentation rules are at that point.
That's the critical takeaway we hope our learner audience internalizes. If you control the identity, you control the cloud. Identity is the new firewall.
There it is.
Shifting your security focus entirely towards strong identity controls, ensuring credentials are short-lived, and implementing granular, auditable permission sets is the most effective and operationally sound way to secure modern infrastructure. It requires shifting from a mindset of, passive network blocking to one of continuous trust verification.
Before we close, let's leave our learner with a final provocative thought, one that pushes the boundary of today's deep dive.
Okay. We spent this entire conversation building systems to prevent unauthorized identities from gaining access and to ensure that authorized identities only have minimal permissions.
Right.
But let's consider the scenario where the bouncer sees a perfectly valid ID and the action being requested is 100% allowed by the minimal IAM role granted.
The identity is legitimate, the key is good, the door lock allows them entry, everything checks out.
Exactly. But what if that authorized identity then performs an action that is technically permissible by its roles, but is damaging or malicious in its intent? For example, a compute engine service account that is correctly granted logging.logwriter permission is technically allowed to write logs.
Mm-hmm.
What if, instead of just writing logs, it suddenly starts deleting critical audit logs that are still pending archival, even though the IAM role technically permits it to interact with those logs?
The system is operating exactly as designed, but the intent is bad. Authorization isn't enough to detect the threat.
This is the essential challenge facing modern security teams. How do we move beyond simple authorization, the check of the ID and the door lock to monitoring the behavior and intent of the identity? How do you defend against authorized malice?
It's a deep question.
And that's where the next generation of security tooling comes in, leveraging anomaly detection, behavioral analytics, and sophisticated security orchestration. It becomes necessary to monitor for deviations from normal behavior, even when the bouncer sees a valid ID.
A truly fascinating challenge that shows security is never static. Thank you for guiding us through this essential deep dive into cloud identity and security.
My pleasure.
We'll catch you next time.